Okay, starting. So far what we have learned, if you still remember about formal specifications, we have a whole bunch of maybe tools, notations that help us to do the specification, like the what we learned, propositional calculus, predicate calculus, and those implication, those notations, no implication and conjunction, disjunction, yeah, and the inference, those things. And so last week, before the break, we learned something about using the Z. Actually, Z is a whole big language. It's more than what we talked in the classroom. So what I want you to do is not only restrict yourself to whatever we have learned in the classroom, but also you can check on this guidelines, those supplementary materials I posted through D2L, so you can have a maybe better understanding of the Z. But for the exam, for the final exam, we will still focus on what we have talked in the classroom. Okay, so about Z, about how can we use Z to specify some system. And one thing I really want you to be aware is the announcement. I also send that through email. So when you look at some answer I provided, it's not the only answer for that question. Okay, remember that. So when I grade your homework or your exam test, what I focus on is the logic and the format. As long as you have that format, you have the logic correctly represented with these notations, with this grammar, with this syntaxes, then I'm fine with your expression. But maybe there are better expressions, like shorter expressions to express the same meaning, that you just need more practice. And when you have a better understanding to that, you will be able to manage to do that. But right now, I just want to see the logic there. Okay. Yeah. So don't worry. Don't worry if you think every time when you are writing a Z specification, when you're feeling struggle for doing the specification, it's okay, because you just started actually, and it's just the logic is not arrived there yet, but it will finally. You will be able to specify a system, a function, or a segment of the system with this Z notification. So that's fine. Okay, and before we start today's thing, so for the rest of this semester, which are only 3 weeks, we will focus on another thing. It's a specification. It's called OCL. Okay. Let me download this to the computer so that I can just open. It's called Object Constraint Language. It's also a language used for specification. Okay, so it's still a specification. And important thing about this is it can be used as a sort of extension to your UML. You know what is a UML? Have you ever learned that, right? We all learned that, right? UML, those class diagram, sequence diagram, those things. Okay, so we can use this OCL as kind of extension to the UML to make the UML tool more powerful and to specify more meaning, to specify more, to express more specification of the system. Okay, so that because if we are using UML, actually most of the time it's quite restricted. You cannot like express all the system with just the UML modeling, right? You can express important things, abstract things, but there are a lot of like kind of extension to the UML. Okay, and if we're using this OCL, it's actually a good way that we use that together with UML. We can formally specify a system. So let's see how can we do that. Okay, yeah, it's there. Okay, so this example using no, we're not here. When I hit the slideshow, it tells me there's only 3 pages here. What's that? What's going on? What's this slide? Okay, MDA. What is MDA? Is model-driven architecture. So it's a framework. Defines how models defined in one language can be transformed into models in another language. So what people are trying to do is we're using some kind of modeling language and trying to use this MDA as a middle layer that can connect, can transform to different language, like what we're using, kind of like English. We translate different language into English, maybe, and then from English we translate to another language. Sometimes we do that, but sometimes it's a direct transformation from one language to another language. But this MDA is something like define how models defined in one language transformed into models into another language. We use something in the middle to do this like adaptation, connection. Yeah. So the MDA process, first you build a model with a higher level abstraction, which is independent of any implementation technology, called this PIM, PIM. Then you transfer the PIM into one or more models to specify your system in terms of the implementation constructs available in one specific implementation technologies. Then you transform from the PSM to the code. So one important motivation we're using more specification is we want the automation of the programming. Okay, we can achieve that somehow, but not the whole thing currently. Yeah, but it's important. It's important because if you want the computer to understand you, you have to have the logic as a computer, as strict as the computer. So we use mathematic way to express those specification. So that's why one of the important motivation of this formal specification. Yeah. So this automated transformation, that's what we want to do, is the key element of MDA to transform and execute it by tools. So when we're doing the modeling, we don't have to do the implementation all the time. We can just doing this automatically. Ideally, we should be able to do that. Okay. Yeah. So benefit of this MDA is productivity. Of course, using tools, we can automatically code a system. The second thing, productivity. I think that's the main benefit. Also, those portability, platform independence, a lot of things has that feature. Like when you're using, when you some programming language Java, a lot of them are platform independent. And cross-platform, of course, the easier maintenance and documentation with the PIM. So that's the some of the benefits. But the main benefit, remember, is the productivity, because we want things to happen automatically. Okay, automatically. Yeah. After we specified. So let's come back here to OCL. That's the main thing we will learn this last several weeks. So OCL, so we need a precision to achieve this MDA-like modeling. Okay, so OCL is actually a specific implementation, a way to implement this MDA, model-driven architecture. Okay, like we use model to do the programming. We use model to implement. We design a model, then implementation is automatically. Okay. Okay, so OCL compared with other formal specification language, the other specification language is difficult to use. They are based on mathematics and have not been widely adopted. So this actually implies the OCL is kind of easy. It's easier than whenever we have learned those mathematics stuff. Okay, and OCL is one solution, standardized and integrated to UML. Okay, that's why we can see it as an extension to the UML, because it's already fully integrated into UML. Okay. So yeah, the relationship between OCL and MDA. MDA is maybe the idea, the thoughts that we want to do this implementation of the system automatically. Okay, and when we are doing the MDA model-driven, we have other details, like it's cross-platform, platform independent, and it can be transferred from one platform to another platform, things like those. And so OCL is one of the possible solution for this MDA. Okay, OCL is a solution. MDA is an idea. Okay, remember that. That may be in the final exam. All right, MDA OCL. And OCL is a textual language of typed expressions based on mathematical sets and logic. You cannot fully avoid mathematical stuff since we are dealing with logic. So mathematics is still something we need to deal with. Okay. Various other formal language have also been used in software engineering. Most such language have proved difficult for average developer to use. The mathematical symbols are not well known and use this different special fonts. Okay, remember this thing. Most such language, for this formal specification language, most of them have proved difficult for the average developer to use. That is true. Okay, if they have never taken this course, formal specification, I think most of software engineering, most of software engineers, they didn't take this course at all. Because first it's difficult, and then it's not popular here. Like I mentioned in the very first class, it's not popular here at all. But it has a value there, and one of the things that prove the application of this formal specification is the difficulty. So, because it's difficult to understand if you have not been trained or not exposed to this thing, and those mathematic notations. Okay, after you learn that, I think it's pretty easy actually. Like we predicate calculus, greater or equal to, less than, and the conjunction, this conjunction, and those things, implication. Okay, after you learn that, it's not that hard. But those notations, we use that less frequently in other areas. So if you're not mathematics major or something, you may not exposed to that at all. So it's difficult. But actually it's not. But OCL makes it even easier. Okay, it's a textual language. We will see some example later. Yeah, so it's something developed by IBM. IBM developed a lot of things, and it emphasized. And actually, IBM, this company, they don't only develop things in the computer science area, but also I visit one of their research center. They also have research in like chemistry, those things. I don't know why, but they do have that. So they do have a lot of research, and this is something developed by them. It emphasizes the precision and simplicity. There's no use of special mathematical symbols, just some general mathematical symbols, okay, which we all understand. Okay. So constraint. With this OCL, we can put some constraint on the UML specification. Okay, let's see how we do that. So what is a constraint? A constraint specifies a restriction on one or more value of an object-oriented model or system. So when you have this UML class diagram, something like this, you have a customer class, and you have this different attributes of it: name, title, age, is male. Okay, so this is the thing, class diagram. Then that's it, right? That's it. But if we want to represent some logic, or put some constraint on these attributes, there's no way to do that in the class diagram, in the pure traditional standard class diagram. However, with OCL, let's see this example here. Okay, so we can put this constraints as expression of a Boolean type, which is pretty similar to what we did in this predicate calculus, right? Remember, predicate calculus, propositional calculus, they are something that of a Boolean type, right? Because we use n, like temperature greater than 1,000 degree. Okay, this actually will return a Boolean value. It's either true or false, right? And maybe valid, reactor active. It's either true or false. It's either active or not, right? Light on, something like that. So here it's the same. So we put this constraint as expression of Boolean type, like here. This is the class diagram. Here we put 3 constraints there. Like age is greater or equal to 18 and age less than 66. Okay, so that gives the range of this age. The range of this age. So this is not something we can easily define with traditional UML. And even more, okay, we have a n. We also have a, so we are not using those conjunction, disjunction. We just use this and, which make it way more easier to understand. Okay, and we have, see here, if else, then, and if. Okay, all right. Let's see. Title string. Title equals to if is male, then Mr. else Miss. Can you explain this to me? Anyone explain this to me? Title.
It's a Boolean, so if is male, then it's either true or false. So if it's true, then Mr. is the title, string title. And then if it's false, then it's Miss.
Yes, correct. So this is actually put a constraint there. Like title, the value of title can only be Mr. and Mrs. And if is male is true, then it's Mr. Then else it's going to be Mrs. Okay. So and this whole thing, we give this value to title, and this can return Boolean value. So title has to equal to that, Mr. or Mrs. Okay, so you can easily understand that without, with the first glance of this OCL thing, right? So that's pretty easy, right? Title equals to, but this logic, you know how to program this logic, right? You just use the if else. And here we can also express that logic here with this constraint, so that it gives you more information about this title. Okay. And name dot size less than 100. So name has a size which should be less than 100. Okay. So we put this 3 constraints there, which are pretty easy to understand. Even you have not learned anything about OCL yet, right? And with these 3 constraints, it largely extends the capability of this class diagram, traditional class diagram. Here we only have the information, the class name, attributes, and the type of the attributes. But now here we have a logic. How can we decide the value of each? Can we decide the value, and what is the possible values? What are the possible values, and what is the range of those values, right? So you get a general idea what we can do with OCL. This is only one thing. Only one. We put a constraint on this attributes, and we can do more with that. Okay, and declarative and typed. So declarative states what should be done, not how. And expression have no side effects. So it's just if you know programming, you declare a type, right? It's similar to that, declarative. And strongly typed means each OCL expression has a type and evaluates to a value or to an object within the system. So a constraint is a valid OCL expression of type Boolean. Okay, that's some attributes here. We can see some examples later. Okay, the states. Okay, so in UML we have several places we can use this OCL. Invariance, so it's a constraint on a class or type that must always hold. So it's also applicable to types and the stereotypes. So it's something very strict you have to hold. And precondition, postcondition, you know all those, right? So we did that in Z. We did that in how can we specify a function, right? Remember those precondition, postcondition. Precondition means the constraint we have to hold before the execution. Postcondition is the constraint we must hold after the execution. Yeah, and the guard means a constraint on the transition from one state to another state. Okay, so this is going to do something with the state diagram instead of only the class diagram. Okay, so that example we just saw is a class diagram, but also we can do that with state diagram. Types in OCL. Okay, so there are some predefined types like the programming language. Okay, so actually it is a language that is higher than the programming language. If you have an experience of using programming language, you should be able to understand this pretty easy, because it also has like a programming language, it has predefined types like integer, right, real, string, boolean, like integers 32, 30, 64, something like that.
What does real mean? Is that
real, like real number.
okay. I've just never seen that type before.
Yeah, but it's defined in this OCL thing.
Okay.
Yeah, maybe you will not use that at all, but
yeah, I was just wondering, is that can you find that in like other programming languages, or?
I guess no, other programming language you use like float,
Yeah.
double, because that's too detailed specified. So float, double, that's all related to how many bits are there in the memory. But here, this OCL is really not for the machine, not only for the machine. Okay, it's not that implementation details there. There are not a whole lot of implementation details there. So like integer, we have int 32, we have int 64, right? But here we only have integer. And this real number here, I think it's can be mapping to those floating, those double things. Yeah, but just we do not care how many like bits are there, how many digits after the point.
Okay.
But it's a real number, so it's aligned with what we learn of the math instead of how they are expressed in the computer. Okay, string and boolean. Collection types, we have set, sequence, yeah, and something else. Yeah, and if you check their specification, their menu, you will see some other predefined types as well, but we may not use them at all here. Okay, and user-defined types, right? Like we define a class, something like that. Okay, so context of an OCL expression. So every OCL expression is bound to a specific context, where self can be used as a reference to this context. Like this. Remember we use this in Java? This is referring to self, right? This. Okay. Okay. And where are we? Okay, this is an example here. Okay, important point here of the OCL is it has to be bound to a specific context. Like sometimes we have more than one class here. Like we have a customer, and then we have maybe a host, a client, some other class. But here we have when we are specifying something, a customer must be between 18 and 66 years old. We have to put this context here clearly when we are trying to specify that. Otherwise, we just do not want to create confusion there, because there may be more than one class. So here, this constraint is put specifically on this customer. So we put this context customer. We have to specify the context, okay? And then the invariant here is, if you still remember what is invariance, so just those constraints we have to hold for this class, right? Self.age greater or equal to 18 and self.age less than 66. Self refers to self, refers to reference to this context, customer. Okay, so this is easy to understand. So customer's age should lie between 18 and 66, right? Yeah, which is so easy. Yeah. So these are some standard operations for this numbers, like real and integer. Equals returns Boolean. So we use this basic operators. I think for most of them we know what that is, right? Anyone do not understand this? Plus, minus, times, right? We all know that. Okay, so and it returns different value for those equal, greater, equal, not equal, less. It return Boolean. Makes sense? And for this plus minus, it return an integer or real. Okay, but for this divide, it only return a real. So why is that? So why it doesn't say integer or real? Can you make a guess? Can you guess?
Why does it say integer or real?
Yeah.
Or which one?
So divide. You see, this plus, minus, multiply, they all return integer or real, right?
Right.
But for this divide,
Because modulus, if you want to get the remainder.
not modulus.
But yeah, I know. Well, modulus is if you want to get the remainder, and then if you want to do integer division, then you get an integer that way. So divide would be real. So you get a float. So that's just if you want to do standard division. So if you got 15 divided by 4,
Yeah.
you're going to get a float. But if you wanted to get the remainder, you'd use modulus. And if you just wanted to get a rounded off integer, you'd do a got div.
Yeah. Okay. Yeah, that makes sense. And also, I'm thinking about something related to this computer. So when computer is doing the multiplication, yeah. So when computer is doing multiplication, anyone knows what happens in the computer, in the CPU?
Doesn't it just add?
Yeah, actually, for computer to do the plus, minus, and multiply, is way easier than this divide operation in computer. So when you are actually doing some a test to your computer, to the capability of the CPU, like benchmark, they calculate how fast can it calculate those divide. Okay, so yeah, it has something to do with the implementation of the divide. So here, all right, that's something not within the scope. But remember that divide returns a real, and the modulus, integer division, absolute value, this maximum, minimum, run, floor, yeah. So all those are pretty easy to understand, right? So that basically all those standard mathematic operations to this values in the which you can use in the OCL. Okay, so those are we are not talking about the conjunction, disjunction anymore, just those general operators here. Yeah, and this OR and exclusive OR, not, we use OR, we use AND, XOR, right? We are not using those notations, but still we need logic there, but so this has to be there. But it's easy to understand because it's close to nature language, right? The implication implies A implies B. Implication A implies B, like this arrow, right? And if then else, we have seen that. If then else, right? Like here. If then else. Also, we have something standard operation for the string. Okay, a string concat, like connect those two strings, a size to lower to upper. It's pretty similar to a program language. You say maybe Java, C#, pretty close to that. Substring means you give a starting index and the end index and take that section out from a string. Equals, not equals, compared to string. Okay, so that's some basic operations we can use when we are doing this. Okay, like we're using this operator here and this operator here. This AND is used to connect Boolean operation. This greater equal is used to use as the operators for real and integer. Okay. Right. Also, we have a collection types and the navigation in OCL expressions. So if self is class C with attribute A, then self.A evaluate to the object stored in A. Make sense? Right. So everyone here use some sort of programming language, right? So this must make sense to you. Like self.A refers to the object stored in A. Okay. Anyone do not understand this? Okay. Okay, that's great. So like C dot A. A is the attributes of C, or A is the member of C. Okay. And if C has one dot 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 association called R1 to another class D, one-to-many association, just maybe one C is associated to many class D, and the association is called R1. Then self.R1 returns a set whose elements are of type D. Okay, let me explain that. So one-to-many association, what is that? Like I have 20 books, I have 10 books, so maybe C is me, myself, okay? And D is a class called book, alright? So from me to book, it's actually one-to-many association. And R1 probably can be the relationship of own. So I own 20 books. Okay, so if I said self.own, it will return a set of books. That makes sense, right? That makes sense. Okay, so if R1 is ordered, then a sequence is returned. Okay, what's the difference between a set and a sequence? So what is the difference between a set and a sequence?
Sets are orders.
Set are not ordered. Yeah, correct. Set are not ordered, but sequence has an order. Okay? So if we have the same elements from 1, 2, 3, 4, 5 in a set, they do not have order. It's just a set from 1 to 5. But if it's the sequence, it has a strict sequence there. 1, 2, 3, 4, 5. Or maybe 5, 4, 3, 2, 1. 2, 3, 1, 2, 4. Okay. So sequence. Yeah. So 1, 2, 3, 4, 5 and the 5, 4, 3, 2, 1 are two different sequences. Okay, because they are ordered, although the members in the sequence, they are belongs to the same set, but they're two different sequences because you have to pay attention to the order. Okay, so that means here this relationship can be ordered. Okay, can be ordered. And if D has the attribute B, then self.R1.B evaluates to the set or a sequence of all the B's belongs to D. Yeah, it's kind of tricky here. It's just a description is not easy, but the logic is pretty easy. It's just self.R1.B. Because self.R1 is a set. Okay, self.R1 is a set. So that may be self.owns, it returns a set of book, right? And B may be the title of the book. So it returns 20 titles of the book I own. That makes sense? Okay, so self.R1 in the previous example is self.R1 returns 20 books I own. Okay, and self.R1.B returns 20 titles of the 20 books I own. Okay, self.R1.B. Okay, those are some syntax there. Associations. This is a one-to-many association from the account to a transaction. So account, you're in your bank account. Yeah, because you spend and you make money every day. You spend money every day, so there are a whole bunch of transactions. It can be in or out. You purchase lunch, breakfast, dinner. So different a lot of transactions there. So self.r1 returns a set of transactions if we are in the context of account. Remember what is context? Context means self refers to the context. Okay, so if the context is account, self refers to the account. So self.r1. R1 is the relationship between account and transaction. Okay, so this is a UML. This is a UML. Traditional UML. You don't see most of the time you don't see this here, but you can somehow see this one to many relations here, like 1 to this 0 dot dot star means it can be from 0 to any number there. Okay, so 1 to many relation. 1 to many relation. One book has many members. One account has many transactions. Okay, so here self.r2, because we define this relation association as R2. Okay, so self.r2 returns a set of members if we are in the context of book. Okay, so this is how we use this in the UML. Okay, clear? Now let's go to this page. Ordered collection. So when you want to navigate into the ordered collections sequence, in this case sequence, what you want to do is just add this keyword ordered there. See that keyword's ordered there, so that when you use self.r1, it will returns a sequence of this okay, so here that's UML, and we put this relation as R1, and we define this is ordered, this account is ordered. Okay, account is ordered, but here its difference is it's many to many. Okay, and then here if we put this context as customer, so now customer is the context. Customer is the context. Well, the self is a reference to the customer. Then if we say self.r1, it returns a sequence of the accounts that owned by that customer. Okay, and it returns an account in some sort of order. That's predefined. Okay, is there any question about this part? No. Okay, so it just tells you something you want to remember is context. Context will define what the what is the self, what is the reference of self. It all depends on what the context you're in. The context is in the customer. Then self means the customer. Self.r1 will refer to a sequence of the account. But in this two example, in the context of account, it will return the transactions. So define the context is important. Okay. Yeah, and functions. So with collection types and also expression, what is the functions? It's expression that states a fact about all object in the collection, or state a fact about the collection itself, like the size of the collection. Okay, so syntax is here, collection, and with this note, the function. Okay, so this is the operations on the collection types. It has the size, count. So this is something called functions. So it stores a fact about object and states a fact about the collection. like the size, right? The collection size. When you return a set of book, if you're using the book function size, it will return like 20. Okay, in that case. Okay, and count the number of occurrence of object in the collection. So you basically you give a book like the textbook. It will count for you how many textbooks there. And includes or, excludes or. It's empty, not empty. Those two are easy to understand. It tests whether that collection is empty or not. Okay, but what is includes and includes or? Excludes and excludes or. So it basically gives you. It's also a test. It returns a true or false value, and you can understand that just from the name of this operation. Includes, and you give a parameter of an object. That means if this object is in that set, if that object presents in the set or collection or sequence. And includes or is true if all the elements of the parameter, if all the elements of the collection present in the current collection. Okay, and excludes is true if the object is not an element of the collection. And excludes or is true if all the elements of the collection are not present. Okay, so exclude, it sounds like we're removing something. We're removing something from that collection, right? And excludes or, it looks like that as well. We are removing some collection from a set. But no, as I mentioned here, what is the OCL function type? Functions on the collection types. What it does is it states a fact, and it states a fact about the collection, and states a fact about all the object in the collection, right? So it only tells you a fact, not doing any operation on that collection. Okay, so for all those predefined operations, okay, none of them is like trying to like remove things or add things. Okay, so that's, we're not doing it here. Yeah, so this is the example of using size and not empty. Okay, do not get confused here. All we're talking about is think about a UML specification, a UML model, which we have two accounts, right? And R1 is the relation between these two accounts. Okay, and now we have another, we know what that is. Okay, now we have another tool called UCL, which gives us more information for that account. Okay, and so here is an example. We're using some specific tools like size and not empty, those two functions of that collection, to specify some constraint for this class diagram. Okay, and here each account can have at most 2 customers. Each account can have at most 2 customers. We cannot do this directly in the traditional class diagram, right? But with OCL, we just need to specify the context is the account, which means the self. The self refers to the account. So self.r1, what is self.r1? What is self.r1? What that returns? So R1 is this relations. First, tell me, when we are doing the self.r1, is it returning an object or is it returning a collection.
What? For the first one?
Yeah.
Second one.
Self.r1.
Guess it's a function.
No, not here. Just this part. Self.r1.
Oh, that's an object.
Object?
Or, well, the property of an object.
It's not an object. It's a set, or it's a collection. It can be a set or a sequence.
Okay.
Okay. Remember here what we talk? You see, self.r1 returns a set here because it's one to many, right? So account has many transactions. When we say account.r1, it returns all the transactions of that account. Remember? So .r1 returns a set .r1. So here it's the same. Self.r1 returns all the customers of that account. Okay, because one account can have many customers. That happens. So self.r1 is a collection. That's why we can use this size, which is a function of that collection, which is function of collection. Right? If it's not a collection, it won't have attributes called size, right? Like a computer.size doesn't make sense because we have only one computer, right? If we have like a set of computer dot size, we know how many. We want to know how many computers are there. Right? So okay, so self.r1 size less or equals to 2. Okay, so this whole thing, these two lines, is a formal specification of this meaning. Each account can have at most 2 customers. Okay, each account can have at most 2 customers. Okay, and another specification in natural language. An account must be assigned to at least one customer. Okay, if I block this part, can I block it? Okay, if I okay, an account must be assigned to at least one customer. Try to do it. We need to have these two parts, context and invariant. Okay, context specify which context we're in. So invariant, inv, specify the constraints. Okay, so here what should be the context? An account, right? Or customer. Customer. Yeah, customer. And what is the constraint there? Customer dot what? We can only dot r1 here. There's nothing else. Right? Customer dot r1. Yeah, we have different ways to do that. We can use the size greater or equal to 1. That is at least 1. Or the it's not empty. R1 is not empty. Here, not empty. So here, okay, account must be assigned to the list. Okay, so it says account. Oh, sorry. So the context here is account, not the customer. Sorry. Because we want to specify that customer is not empty. Yeah. So we are in the context of account. So self.r1 is not empty. Actually, self.r1 in this and sub.r1 in this, they are referring to the same set. And this set should not be empty, and this set should be of the size less or equal to 2. Okay. Anything unclear in this page? Come on, ask the question so that yeah, because this is actually not difficult. So anything unclear? Clear? All clear? Okay, nice. Okay, let me ask you a question again. So self.r1, which returns a set, a collection, right? It can be a set or a sequence. Yeah. Self.r1 returns a collection. And collection has all those operations, size, not empty. Right, remember? Okay, size, not empty, and some other thing, some other there. Okay. So this is another interesting example. Okay, so here we have a two class called flight and person. Flight and person. Okay, and there are a whole bunch of relationships between the between the flight and the person. R1, R2, R3. Okay. So R1 is a 1-to-1. Basically, it specifies the pilot of that flight. And the R2 is the crew members. Okay, and R3 is the flight to the flight attendant. Okay, remember those. R1 is the pilot, I2 is the crew member, I3 is the flight. Okay, so flight is piloted by the person, which is pilot, and R2, the flight, has crew member, which is a whole bunch of person, and R3 has a flight attendant, has flight attendants. Okay. Now let's see here. If we want to specify a pilot is a member of the crew. Okay, here we cannot specify that a pilot is a member of the crew with the class diagram, right? And now, with the help of OCL, we should be able to specify first a pilot is a member of the crew. How can we do that? Let's go back here. So the question is, a pilot is a member of the crew here. Let's see. First, we need to have a context, right? Context is flight. Okay. Context, flight. Okay. What is the other thing?
In IMV, I forget what it's called. What's it stand for again?
R2, yes. This actually, this part will return a collection of the crew members. Right, crew members. Okay, and then this collection
has include.
includes,
Includes.
yes. Include or includes R?
Includes
Includes.
a pilot, so we are include. Include.
So, okay, so include, what is inside this include? You cannot just say pilot, because it's
Island.
not there. Pilot is not anywhere on this class diagram.
R1.
So, you have to find that.
That's not that hard.
Okay. So yes, correct. So it's self.r2 includes self.r1. Okay, I forgot the s. Alright. So the second, all flight attendants are also crew members. All flight attendants are also crew members. Is it similar to that? Right?
Be the same thing except R3, right? Instead of self.r1.
It's similar, but instead of includes, we're now using includes or. Right?
Includes or?
Yeah. Let me show you. Here. Because self.r3 returns a collection.
Oh, includes all.
Yeah.
Okay, sorry. I thought you meant like the or operator.
Oh yeah,
I
oh
was
sorry.
kinda confused
Not
about
or.
that.
All. Or.
Okay.
All. Yeah,
That's
includes
alright.
all. So includes all. R self.r3. Yeah. So that's the difference between includes and includes all. Right? Okay, select, reject, collect the sum. We still have this select, reject, collect and sum we can use for the collection. Okay, then let's do that on Wednesday, right? All right. Thank you very much for coming today.